Thank you. So I'll just continue the lecture in the same slides. So now I will introduce the Beilinson-Bloch conjecture, which is a higher dimensional generalization of the BSD conjecture. So from now on, we will take an even positive integer n, which I will write as n as 2r. So let K be a number field, and the Kx will be a projective smooth scheme over K of all the dimension n-1. Okay, and we have there's an L function for the middle degree cohomology Hn-1 of xk bar, the L function, and for every rational prime L. And this L function is conjectured to be meromorphic. Has a meromorphic continuation to the entire complex plane and is independent of L and satisfy a functional equation with center 0. And the unrefined Beilinson-Bloch conjecture predicts that the order of this L function at the center x equals 0 should be the rank of the codimension R cohomologically trivial Chow group, which by the previous Beilinson-Bloch conjecture, this has finite rank. But this is a finite number. And of course, this is also a finite number, and they should be equal. And this should hold for every L. So when X is an elliptic curve, this simply recovers the unrefined BSD conjecture. Okay, because in the BSD conjecture, this cohomology is same as L-adic Theta module. Okay, so this is the usual L function for elliptic curve up to some translation. Okay, there is also an equivariant version of the Beilinson-Bloch conjecture as follows. And suppose that X admits an action of some algebra T via étale correspondences. Then T will act on both the cohomological trivial part of the Chow group and the cohomology. Okay. Suppose we are given a non-zero irreducible finite dimensional complex representation rho of T, and then for every prime L and every embedding QL into C, there is an L function which is just the rho isotypical part of this cohomology, and just this the L function of this isotypical part. Then the equivariant version of this conjecture predicts that both sides should equal under this isotypical part. So the isotypical part of this cohomological trivial Chow group should be the dimension of the rho isotypic part should be same as the order of the L function of this isotypic part at the center. Okay, and this can be regarded as the Beilinson-Bloch conjecture for a Chow motive, this isotypical part of this motive, and this Hn-1 is the conjectural Chow motive of X of degree n-1. Okay, so this is an equivariant version. Of course, we stated without using conjectural motive. And now we want to specify this equivariant version of the question. Seems also has a question.
So you said the null correspondences, but is it really important, or you can just have all correspondences of a given dimension? This should also be.
Oh, my étale correspondence by definition is the degree 0 correspondence. It's the
okay, but is it needed here to have a étale correspondence rather than more general correspondences?
Oh yes, you can state it in more general way. You're right. But
okay.
for my particular application later, it's all like but only involve étale correspondence.
Okay, and then
for simplicity.
I want to ask just about the case of like modular curves and Hecke operators. So is it really étale correspondence, or in the cusp there could be something non?
So for head correspondence, for the model, if your head correspondence is away from that local, for example, if it's a p-adic model and your head correspondence is away from P, then it's even a tau on the model. But if the head correspondence is at P, then the integral extension is not a tau in general.
Okay, no,
so we will only use it correspondence away from the characteristic of the model. So.
No. I was thinking about the cusp of the modular. Okay, this.
Okay, so let us specify the equivariant version of this Beilinson-Bloch conjecture to certain unitary Shimura varieties. So from now on, we fix a subfield E of C, that is a CM number field, and we take F to be its maximal totally real subfield. And we introduce a notion, we say a Hermitian space V over E of rank M is called a standard indefinite if it has a signature M-1, at the default embedding F in R, and a signature M0 at other real places. Okay. And for a standard indefinite Hermitian space V over E of rank M, we have a system of Shimura varieties XL indexed by sufficiently small open complex subgroups L of this finite adelic point of H. Here H is the unitary group of V. And these Shimura varieties are smooth quasi-projective of dimension M-1 over E. And they have a complex uniformization like below. Here, the symmetric domain is this one. So that's PVC minus is the subset of PVC. So this is the projective space of VC. In particular, this one has dimension M-1. And this is the complex open domain of negative definite lines. Okay, negative definite lines. So this one has signature M-1. So you can talk about the negative definite, that there are such lines. Okay? And such lines form an open, complex open ball. And here is the conjecture, the Beilinson-Bloch conjecture for unitary Shimura varieties. Let pi be a tempered cuspidal automorphic representation of GRAF. Here, this GR denotes the quasi-split unitary group over E over F of rank n equal to R. Okay, so this is usually people call it URR. And if you don't know what tempered means, that's fine. You can just ignore at this moment. And let V be a standard indefinite Hermitian space over E of rank n. So this n is same as n here. Okay, and we denote by H, it's it's unitary group. Now for every irreducible admissible representation pi tilde infinity of this finite adelic point of H, satisfying the following two conditions. First, I want this pi tilde is nearly equivalent to pi, which means that they are same for all but finitely many non-Archimedean places V of F at which HV is isomorphic to GRV. Okay. Second, I want this pi tilde to appear in the middle cohomology of the system of Shimura variety XL. So in short words, I want this pi tilde to be nearly equivalent to pi and also appear in the middle cohomology of the Shimura variety of V, of H. And what's the consequence? The consequence is the following. So what is the multiplicity of this pi tilde appear in the cohomologically trivial part of the child group of codimension R? Okay. So what's the multiplicity? The multiplicity, which is same as the dimension of this home space, should be the order of this automorphic L function at the center, which is half. I mean, somehow the automorphic convention is that the center is half, and the arithmetic convention is that 0 is the center for polarized motive. Okay. So this is the conjecture. So there is a annoying notation here. So so let me first explain what this is. So here, this bigger pi tilde infinity is the cuspidal factor of the base change of pi. The base change of pi is the automorphic representation of GLNAE. So it's a representation of a general linear group determined by tilde via other multiplicity formula. Okay, so for those who are not familiar with automorphic form, you can just assume that the base change of pi is already cuspidal. Okay, this is called a stable case. If base change of pi is already cuspidal, then there's only one factor, and it's just the whole base change of pi. So there's no ambiguity here. Okay. So that's the conjecture. So you may be a little bit wonder why this is the consequence of the Beilinson-Bloch conjecture. So let me explain the relation. So any question at this moment?
Yes, that's one question.
Oh, there is a question.
Why do you focus on the standard indefinite case?
Oh, you mean why choose this signature? Is this your question?
Yes, yes.
Okay. So here's the reason. So what we really want to study is the motive of the Galois representation attached to pi. Okay. So you want to see, at least you want to see the Galois representation of pi. And such representation will appear on Shimura variety of some inner form, pure inner form of GR. And only when the pure inner form has this kind of signature, you will see the Galois representation. Otherwise, if, for example, if you take n-2 here, then you will see a wedge square of the Galois representation instead of the Galois representation. And if you take n-1 at one place and n-1 at the other place, you will see a tensor product of the Galois representation and its twist. So only this signature, you will see the Galois representation itself without any operation on it. Okay, does that answer the question?
Yes.
Okay. Mm-hmm. Let's continue. Okay, that's the maybe okay, I will explain maybe later why this recovers the. Okay, I think this is sorry. This one is easy. This is an example of this one here because you just take a T to be the Heck algebra, and you take a rho to be the pi tilde the fixed as a Heck module. Okay, and then you will recover the Beilinson-Bloch, the equivalent version. Of course, you need another ingredient to see that. Okay, at least the one base change pi is cuspidal. This recovers the Beilinson-Bloch conjecture, equivalent version for Shimura variety. And more general, it requires some computation using Arthur's multiplicity formula. I will omit because it's quite technical. So let me give some background on automorphic representation.
There was one question, Yifeng.
Yeah, yeah, please.
But when the field F is Q, the Shimura variety is not projective. And
yes.
you only stated the Beilinson-Bloch conjecture for projective varieties.
That's great. Okay, that's a great question. I'm a little bit lazy here. So when F is Q, there is a canonical smooth compactification of XL.
Oh, so you are using that compactification?
Yes, there is a canonical one. There's a canonical smooth toroidal compactification.
Oh, you are using toroidal compactification.
Yeah, there's a smooth canonical one for XL. So I'm using that XL in this conjecture. Yes.
Oh, okay. Thank you.
Mm-hmm. Okay. So let me review some. Okay, let's still record the notion. So N is 2R, and we have fixed the CM subfield E with F the maximal totally real subfield. And we give more notation to this GR. So for any positive integer M, we equip Wm, which is e to the 2m, with the skew Hermitian form given by this standard matrix. And we put Gm as the unitary group of the skew Hermitian form, a skew Hermitian space, Gm. And this is a quasi-split reductive group over F. And note that the Gardon subgroup of Gm is the restriction of scalar of GL1 from E to F and M top base of it. So for every non-Archimedean place V of F, we will denote by this KMV to be the stabilizer of the lattice OEV to the 2M. There's a natural lattice here. And this is a special maximal subgroup. And in what follows, we will consider a cuspidal automorphic representation pi of GRAF satisfying the following three conditions, just for simplicity, okay, mostly for simplicity. So, so first, okay, I shouldn't say this. Okay, let me first introduce the three conditions. So the first one, if V is an Archimedean place, I want this pi V to be a holomorphic discrete series of this particular weight. If you are not familiar with this language, you can just think this as the higher dimensional analog of holomorphic of weight 2. Okay, you know that the weight 2 is the smallest weight of a holomorphic discrete series for GL2. And this is also the smallest possible weight for holomorphic discrete series for URR. Okay, and just think about this as minimal weight. Okay, it doesn't matter. So if V is non-Archimedean and non-split in E, we want K pi V to have KRV invariance. So in other words, it's KRV spherical. So this invariance is non-zero. And it must have dimension 1 because this is a special maximal subgroup. And in general, at a non-Archimedean place, I want the pi V to be tempered. Tempered means there are many equivalent definitions. So I will give a quick one. Tempered means this is contained in a parabolic induction of a unitary discrete series representation. Okay. So we're basically, so this is a minimal holomorphic discrete series minimal weight. And this is a KRV spherical for non-split places. And this is tempered everywhere. So this is just three conditions. And in R1, a holomorphic discrete of weights, this blah blah weights means that it is isomorphic to a constituent of the normalized principal series. This one, I mean, the Gardon is this group, right? This is the minimal possible weights for a holomorphic discrete with trivial central character. In R2, since pi V is KRV spherical, there exist unitary unramified characters, chi V1 blah blah to chi VR of EV cross to C cross. They are unique up to permutation and inversion. Okay, they're unique up to take permutation and taking inverse, such that chi V is isomorphic to the normalized principal series of these characters. Okay, and we will use this chi V later a little bit more. So just keep in mind that this chi V is the Satake parameter of pi V. Okay, now we define the standard L function. We now define the complete standard L function, Ls pi, as follows. When V is Archimedean, this Ls pi V is defined as the product of this L function. So what is arg? Arg is the so-called argument character. So this is a L function for C cross. So you can find the definition in Tate's article. I mean, Tate has an article called what? I forgot it. There's a famous article like defining all these local factors. And just take a product from I to 1 to R. Okay, that's the Archimedean factor. And when V is non-Archimedean and split in E, we define it, which is similar to the one, but instead of using argument character, we use this Sadake parameter character, chi VI. It's chi VI inverse, I from 1 to R. And you can easily see that the whole product is also unique, is also independent of permutation or the taking inversion. So it's intrinsic to pi V. When V splits in E, we define L as pi V to be the product of two factors. There are two of such U, where the product is taken over two places of E over V. And the pi U is simply pi V, but regarded as a representation of GLNE U. So there's just GRFV is isomorphic to GLNFV through two ways. I mean, each U will give you a way. So this one is through the one that's given by U. And we have another one like U prime. And the relation between pi U and pi prime is that they are contragradient to each other. Okay, so in particular, the product depends only on pi V. And as usual, this L S pi, the whole product is absolutely convergent for the real part sufficient large and has a meromorphic. And actually, in this case, it's a holomorphic continuation to C, and it is satisfied the functional equation, which is Ls1 minus S pi equals epsilon S pi Ls pi. And the center of this epsilon factor, the center of the epsilon factor equals to -1 to the R times the degree of F over Q. Okay, so it's easy to compute. It's this one. So in particular, the vanishing order of Ls pi at the center half has the same parity as R times the degree of F over Q. Any question? Okay. For experts, this L function is same. I mean, from the definition, this L function is the base change L function. But in this case, one can show that this L function is also the doubling L function, the PSR doubling L function. Okay, they coincide in this case. Okay, so what we are going to do with this pi? So when R times degree of F is even, we will study the central value via the, because in this case, the order is 0, the vanishing order is even. So it is possible that the central value does not vanish. And we want to study the central value via the classical theory of theta lifting. That's a very, that's a very flourished theory like from 1970. We will recall. And this is a new story, a relatively new story. So when this product is ordered, so that the vanishing order is ordered, in particular, it vanishes at the center. So we are motivated to study its central derivative, L prime, via the theory of so-called arithmetic theta lifting. So for further use, we will introduce some notation. So for positive integer m, we denote by Herm m as the subscheme of Hermitian matrices. Okay, and we will by Herm circ as the invertible Hermitian matrices. Okay, and we by Herm m f plus and the Herm m circ f plus. Plus means the totally semi-positive or totally positive definite elements, respectively. Okay, so I think this notation is quite suggestive, or you don't have to remember. Okay. I mean, you don't have to memorize it. It speaks of itself. Okay, let's continue. So the rest of the talk, we will start from this story today first. So, but let me first review the construction of a wave representation. So this is a foundation to study this doubling, to study the theta lifting. So let's fix additive character AF to be the standard one. So namely, this is the one satisfying that its component at any Archimedean place is given by the e to the 2 pi x. Okay. And for every positive integer m, every place v of f, and every non-degenerate Hermitian space vv over ev of dimension n. So this n is always fixed. This m will change according to our needs. Okay. So the Hermitian side always has rank. I mean, here is always n. And we have the representation called omega mv of this product group, the GMFV and the unitary group of VV, FV points on the space of Schwarz function on the VV to the m's power defined by the following formula. So, I mean, these are well-known formulas, but I will just recall for convenience. So we first define the action on the GM side. We first define the action on the Levy part. On the Siegel parabolic part. So for A in GMEV and a function Schwarz function phi, the action on phi is guided by a translation of x by A and scaled by this factor. And for B, for the unipotent part, the action is just by a scaling by the trace by an additive character. Okay, here this Tx is defined as the, oh, sorry, I forgot some, maybe no. So this is the pair, the Hermitian pair on V. Okay, sorry, I forgot there should be VV here. A Hermitian pair on V is so-called the moment matrix of X. Okay. And X is an element in VVM. And this is the entry, ij entry is the pair between xi and xj under the Hermitian pairing on VV. It's called a moment matrix, and apparently this is a Hermitian matrix. The third, for this vial, longest vial, for this vial element, the action is given by a Fourier transform. So here, there's also a factor gamma VV to the m. This gamma VV is a very constant. It's either 1 or -1, depending on whether VV is split or not. And for, okay, these three together will give you the action of GMFV because they generate the whole group. And for H from this group, the action is easy just by translation, by left translation. Okay, so the action on phi is just phi H inverse X. So these are like well-known formulas. Okay, now we discuss what happened when the root number epsilon half is 1. In other words, we go back to the automorphic representation pi of GRAF and assume first that R times the degree of F is even. Okay, we always assume our pi satisfies R1, R2, R3, just for simplicity of the talk. In this case, because this number is even, we have a Hermitian space V of E of rank n, unique up to isomorphism, that is totally positive definite and split at every non-Archimedean place F of F. This is an exercise in Hasse-Minkowski theorem, like a local global principle for Hermitian space. Okay, that's an exercise to show there is a unique such Hermitian space. And we denote H by its unitary group. Now for every full adelic Schwarz function phi on VR tensor AF, this is the full Schwarz space. There is a theta function, or the theta phi GH. This is a function on the product group. And the definition is easy. You just average the function phi over all rational points in VR, but together with an action. And you use the Weyl representation to twist your phi, and you take sum over all x. Okay, and the same as, because the action of H is simply by left translation, this is also this one. Okay? And so this is an infinite sum. You can show that it's absolutely convergent. And more than that, it gives an automorphic form on GRAF times HAF. I mean, the invariance on HAF is automatic, right? Because it sums over all rational points. The invariance on GRAF is the application of Poisson summation formula. Now we go back to our representation, automorphic representation, cuspidal representation pi, and we take a vector phi, var phi. Sorry, there are too many phi. Var phi. It is today we know that this representation pi has a unique realization in the space of cusp forms of GRF. So it doesn't matter how you embed. There's only one embedding, okay, of pi. Up to scalar, there's only one embedding of pi. So we take a cusp form var phi, and we convolute the theta kernel with var phi or var phi bar on the first variable, on the first factor. So you integrate this var phi together with the kernel function over GRF over GRF. Okay, and this is because this is a cusp form. This integration converges and it gives you a complex number for any h. For any h, and you can show easily that this is an automorphic form on HAF. So you like a kernel here. You lift autoform form on one group through the theta kernel and descends to another group. So this is a standard kernel operation. Okay. Of course, the question of this operation is that so first, is this function trivial or not? Maybe you just get zero, right? You just get zero. If no, what else can you say about this function? So answering this question, that's a famous theorem of Rayleigh's obtained in 1980. It's called the Rayleigh's inner product formula. Actually, the original, the original formula covers this one. Okay, so suppose we are taking this var phi, which are decomposable over all places. Like we consider two of them. Okay, phi 1, phi 1, phi 2, decomposable. And we also take two cusp forms in pi, also decomposable, var phi 1, var phi 2. Then we have two theta lifting, the first one, the second one. And we take a Peterson inner product of them. And you should get a complex number. What is that number? This number is this quantity. Okay, so the important one, the one that's coming to your eyes first, should be this one. It's the central value of the representation pi. And there's another constant here I will define. And there is some local contribution I will also define. Yeah. So just wait for a minute. In the next page, I will explain the undefined notion here. So just keep in mind the form of this formula, a pairing on the left-hand side, and on the right-hand side, a central value times some local contribution. Okay, that's all you need to memorize now. We explained the notation in the above theorem. So here, this bracket H denotes the Peterson inner product of automorphic forms on HAF with respect to Tamagawa measure. Okay, with respect to Tamagawa measure. And this Bn some abelian L function. So this is a product of local one, and the Bn, the local one is the local L function of this eta v to this power and at this value. So this eta is the automorphic character associated to the quadratic extension. So this is a quadratic character. Okay, this is corresponding to this extension via global class field theory. And this CV natural is so-called normalized doubling theta integral. So the CV natural is the following integral. It is the integral of the product of two matrix coefficients. So you have pi v, right? You first, sorry, there's no GV here, it's a typo. You first, this is a matrix coefficient for pi v. This is a matrix coefficient for the V representation, and you take like a convolution of both. And this is absolutely convergent, one can show. And you normalize this integration by the inverse of the local counterpart of this L function. So in other words, the mysterious L function coming out here is just the product of local normalizing factor. And why do you normalize this? Because at all but finitely many places, the value of this integration is same as this local L value. So when you invert this term equals 1 for all but finitely many. So what you get here is a finite product, although I wrote it as an infinite product. It is actually a finite one. This is a standard operation called normalization in this infinite product. Okay. Any question for the theorem? For notation or for the content of theorem? Okay, if no, we continue a remark. So you see, if you look again this theorem, what are the thing on the two sides? So this term is a functional on phi1, phi2, var phi1, var phi2. And on this side, this product is also a functional on var phi1, phi1, phi2, var phi1, var phi2. And this is a constant that depends only on pi. It has nothing to do with this var phi and phi. Okay, so and these two functionals, the left side one, the right hand side one, they actually define two elements in the following space. The space is the following. So if you take the H co-invariance of the Schwarz space SVV2R, okay, this var phi1, var phi2 will give you elements here by taking tensor. And the phi1, phi1v, phi1, phi2 will give you the dual of the element here. Okay, and you can check this home is invariant under GR times GR action. So this is an invariant functional here, and it runs over all V. Okay, this is a it looks complicated. However, it is known that each vector for each V, this home space is one-dimensional. So each vector space is one-dimensional. So the tensor is also one-dimensional. This is a one-dimensional space, complex linear space. And moreover, this product gives you a basis of this one-dimensional space. It's non-zero. This is a non-zero element in this vector space. So since this space has dimension 1, this element must be a multiple of this element as a functional, right? As a functional. And what is this constant? What is this proportion? This is exactly what Rayleigh's inner product formula tells you. The formula just tells you that the proportion of the two invariant functionals is this one, is this constant. Okay. So in particular, it is independent of phi and var phi because it's a proportion of functional. Any question? Okay, let us sketch the proof of Rayleigh's inner product formula because we will use this idea to study the arithmetic counterpart later tomorrow. The first step, because this one is called a doubling method, you need to double something, right? The doubling applies on the skew Hermitian side. So we now take, so for simplicity, I will just double the group rather than doubling the space. So we will consider a larger unitary group G2R. And GR times GR will be a subgroup of G2R via disembedding. Okay, somehow you need to twist the second one by a negative sign here. And so the first step, the second step is to use the Siegel-Weil formula to transform this inner product on H, the Peterson inner product on H to certain Eisenstein series. So here I'm regarding this second variable is a function in H. and allow the first variable G1 to change. Okay, this is the Peterson inner product of the theta kernel for any given G1, G2 in this group. So in particular, this should be a function in G1, G2. And what is this function? This turns out to be an Eisenstein series. So let me recall what is this Eisenstein series. Here, for every phi Schwarz function that in the double of this VR, so V2R, we have the Siegel Eisenstein series, the following one. It is the, so here you use the doubling Weil representation of G on this group, okay, because it's 2R here, so it's on this group. You act on phi and you take a value on 0, and this one is invariant under the parabolic, and you take sum over all the left coset here, and you weight it by a certain height function, h. So h is denotes height function with respect to P2R. You get an Eisenstein series. This is a typical way of defining Eisenstein series. I mean, this is essentially, if you take R equal 1, I mean, this is similar to the classical Eisenstein series you define where you in for GL2. Okay. Now you take S to be 0, and you take a G to be G1, G2 embed here, and you take a bigger phi to be phi1 tensor phi2 bar. It should give you the Peterson inner product of the theta kernel. That's called the Siegel-Weil formula. So now, so the original left-hand side here, instead of convoluting over G first, you first take you can like change the order of integration. You first take Peterson inner product on H, then you convolute along G1 and G2. So in other words, you first take Peterson inner product on H, which you get an Eisenstein series. Then you convolute along G1 and G2. So the original term here is the same as this double integration now by the Siegel-Weil formula. And for this integration, there is a standard expansion procedure by the cuspidality of var phi1 and var phi2. And this expansion procedure will eventually lead you to this identity. Okay, I'm omitting lots of steps here, but eventually it will give you this quantity. And the whole thing is a long process of calculus. Okay, so that's the main steps, just 3 steps. Okay. Any question on notation? Because we will use Eisenstein series later tomorrow, so it's better to have a feeling on at least make sense of it. The definition, notation. Okay, so I still have 10 minutes. So I will make some preparation for tomorrow's talk. Okay, so it's about a special cycle, Kudala special cycle, and the generating series. They will play the role of theta kernel tomorrow. So let me just review. I mean, these material are well documented in literature, but I will just review for simplicity. So special cycles and a generating series. So we will just take any standard indefinite Hermitian space V over E of rank n, which is 2R, and we denote H as its unitary group. And then we take a neat open compact subgroup L, a sufficiently small open compact subgroup L, and we first record the construction of Kudala special cycle DXL for every element X in this finite adelic Hermitian space. First, if the moment matrix of TAX does not belong to this subset, we set it to be 0. Okay. Second, if the normal matrix is rational and is totally positive definite, then in this case, by Minkowski principle, we can find a rational element Y in Vm. And sorry, I should say m is less than n minus 1 maybe. Okay, it's fine. So we can find a rational element y in Vm and an element h in the final adelic point of the group such that hx equals y. Okay, you can always translate your x, how to say, some F2 elements have the same moment matrix, you can translate them. Okay, so you can translate x to a rational element. Originally, x might not be rational. Y in Vm, not. Oh, right, it's Vm, yes. Now we denote by Vy the orthogonal complement of the subspace spanned by components of V in Y. Now, because Y is totally positive definite, so the complement is also standard indefinite. Okay, and its rank is n minus m. The rank is n minus m. And we put hy as the unitary group of Vy, which is naturally a subgroup of H. And we denote CXL to be the image cycle of the composite morphism. So first, you conjugate your level L to HL H inverse, and you intersect with the subgroup HY. So this one will give you a natural morphism which is induced from a map of Shimura data. And this map, you can see that it's a finite and ramified map. And then you use H to translate this level to the original level L. And this map is a tau. So totally, it's a finite and ramified map. Any finite and ramified map will define a cycle in XL, in an algebraic cycle, simply by push forward. Here, XY denotes the system of Shimura variety for Vy. It is straightforward to check that CXL does not depend on the choice of Y and H. It only depends on X. Moreover, CXL is a well-defined element in the cycle group, in this codimension M cycle group of XL. Okay. And there's another degenerate case. So for Tx, suppose that Tx is rational, but not necessarily totally positive, only totally semi-positive. Then there's also a similar cycle, but only well-defined in the Chow group, not well-defined in the cycle group, okay, in the Chow group. And the definition is a little bit more complicated than here. And since we will not use this precise definition, we omit. For those who are interested in, you can go to Kudla's original paper on special cycle or any paper on special cycle. Okay, now we need to take average, take a weighted one. So we take any Schwarz function, the finite adelic Schwarz function that is fixed by L, and a moment matrix, a Hermitian matrix T. We put CT phi L as the weighted average, weighted sum of all CXL weighted by phi X. And this X goes through all VM tensor F, AF, the finite adelic, this set, and modeled out by L. And we require that the moment matrix of X is T, a given T. And you can easily show that this indexing set, you can easily show that this indexing set is finite. Okay, and this is a finite sum. Okay, so this is a well-defined element in the Chow group. Now, if we assume that T is a totally positive definite, then each term is actually in the cycle group. So this is even a well-defined element in the cycle group, tensor over C. Okay, so it's even better. There's a physical cycle you can see rather than a mysterious Chow cycle. Okay, so a little bit notation on automorphic form. So we will, in what follows, we will denote by ARGM the space of automorphic forms on GMAF of parallel with R. So I will not give you a rigorous definition. So what does it mean? Recall that for modular form, you have automorphic factor, right? This is like a character of the maximal compact subgroup. And the weight is defined as a power of that character. So in the URR case, there is also an automorphic character. And the parallel with R means that at every Archimedean place, the open compact subgroup acts by the R's power of that automorphic character. You don't need to know the precise definition, it doesn't matter. Okay, so for any var phi in this space, there is a Siegel free expansion, which generalizes the usual free expansion for modular form. The free expansion is indexed by Hermitian matrices of rank M. Okay. So it's right, phi t times a qt. Qt is just a formal symbol. And this phi t is some Fourier coefficients like this. So here is a conjecture due to Kudela, known as the modularity hypothesis. The hypothesis says the following: for any Schwarz function that is fixed by L, there is a holomorphic element which is uniquely necessary by the property it satisfies. I call this a fancy Z phi infinity L in the tensor of the automorphic form space with the child group space, such that for every finite adelic element G of the skew Hermitian, of the unitary group GM, the Siegel Fourier expansion of the shift of this Z by G coincide with this Q expansion. So the coefficients, you can just take a G to be 1 for simplicity. So this is a child group valued automorphic form such that its T's coefficient of its Siegel free expansion is given by the weighted special cycle. Okay, that's the modularity, the meaning of modularity. In some words, this formal Q expansion is modular. And this conjecture is formally known, i.e., if you ignore the issue of convergence, the modularity is proved in my thesis. And this convergence issue is still open today. Okay, so rigorously, it is only known when M is 1. When M is 1, it is known. The convergence is known. But for higher M, the convergence is still open. Okay, so I will stop today. Tomorrow, we will continue the arithmetic story when the root number is -1. Okay.
Okay. So are there any questions? So maybe in the online participants also? No? Okay. So I have one small question then. Do you really need to assume that the automorphic representation is tempered everywhere for Alice in a product formula?
For Rice in a product formula. No, for this one, let me see. For this one, I think no. I think no. You don't need it. You only need a cuspidality. Right?
But do you need an assumption like that the parameter is generic?
Okay. There is one issue. One issue for non-tempered one is that this might not be convergent.
But if the parameter is generic?
Oh, you mean do you need the physical temperedness of the?
Yes.
Parameter. I mean, I think once you have convergence of this one, then it's okay. For the convergence of this one, do you really need a tempered? Probably no. You only need it is in some strip, right?
Yeah.
Yeah. Then as long as it's in that strip, it's okay. The only issue is the convergence of this local.
Okay. Thanks. Other questions or comments? So if not, let's thank Yifeng again.